All right, so my name is Chaneil Wallace. I'm a postdoctoral researcher at Laurentian University, and my work involves looking at trace elements in quartz to hopefully address the issue of intrusion-related versus orogenic gold deposits in the Superior province in particular. So the distinction between intrusion-related and orogenic gold settings has been an issue since these terms were introduced a few decades ago. I won't go over these differences in details, but in general, intrusion-related deposits have a main intrusive center and form in a higher level setting, less than 5 kilometers. And in contrast, orogenic gold deposits are related to regional deformation and metamorphism and form slightly deeper from 6 kilometers and greater. This distinction is pretty easy. Distinction is easier in Phanerozoic settings, but it's a lot more difficult in your older Archean settings like Superior because the field relationships are a bit more ambiguous because of all of the later overprinting deformation and metamorphic events that may or may not have been related to the initial gold mineralizing events. So this leads to the hypothesis. Can quartz chemistry be used to differentiate between orogenic and intrusion-related gold deposits? So in recent years, laser ablation has allowed us to do trace element work in a whole suite of minerals, and this has allowed us to do things like fingerprint-causative fluids, an indication of fertility, and even differentiate deposit types. So for example, pyrite chemistry has been used to constrain and understand the nature of ore fluids, and to differentiate deposit types. So from Gregory et al., so things like VMS versus porphyry deposits, he's used trace elements and probably to differentiate those deposit types. But also quartz trace elements have also been used to differentiate between magmatic and pegmatitic systems from lower hydrothermal settings. But in addition to the trace element work, CL also needs to be coupled to trace element work. So CL is very important in identifying different zones for your laser ablation work. And there are very few studies, I would say, that have done CL work on quartz from orogenic settings, in particular in older orogenic deposits. The CL itself can be very informative and tell a story because the CL reflects physical-chemical changes. And so, for example, with this sample from Macassa, we can see a zone CL response in a deposit which has been described as an orogenic deposit. So just a quick, simple background on quartz. Typically, substituting for silica, we have lithium, aluminum, titanium, and germanium. Lithium and aluminum typically occur as a Kupel substitution for silica. There are also different oxygen and silica vacancies that you see in quartz structure. Titanic Q is a geothermometer that was modified by Wang et al. And basically it says it uses titanium in quartz to determine the temperature. So basically higher titanium in quartz equals higher temperature. So it would be expected that titanium in intrusion-related gold systems would be higher than in titanium in quartz from orogenic systems. Typically aluminum, germanium, lithium, they mostly increase with progressing fractionation of a melt if there's a melt involved. So typically you would see aluminum, germanium, and lithium higher in lower temperature systems. So that's a brief background from Rortier and Casanova. So what they did is they compiled a lot of data from different quartz trace element studies that was available to them at the time. So I won't go over all their elements, but just to focus on titanium. They have volcanic magmatic quartz, so from the host rocks of these systems, quartz and host rocks. And then they looked at different veins from porphyry copper deposits, so different vein types that progress during the evolution of the porphyry systems. So what we see here is we go from higher titanium straight through to lower titanium, which based on Titanic, you would say we have decreasing temperatures. And then we have epithermal systems here. So we go from high to low in these systems of titanium, which makes sense and which proves that using titanium, for example, in quartz might be useful in differentiating, or has the potential to differentiate intrusion-related from orogenic deposits. So I won't go over all of the different settings, but there are about 39, 40 different deposits I looked at. About 25 of them were from Superior. So the bold red deposits are the ones in Superior. So For the data set, I looked at magmatic quartz, so quartz in the host rocks for these systems, like Magino and Code, et cetera. And then we also looked at a pegmatite system from Nova Scotia, a porphyry copper from Nova Scotia, various intrusion-related systems across Superior, orogenic systems in Superior, and then one epithermal deposit. So just to show you in general, we have samples from Swayze, from Kirkland Lake, Val-d'Or, a sample from Val-d'Or, et cetera. So most of the samples could come from the Abitibi. We also have some samples from Wawa, so like Eagle River, Magino, Renabi. In this case, unlike in the Abitibi, we have a mixture of intrusion-related and orogenic systems. Most of these samples that we collected came from the deposits that are assumed to be intrusion-related systems. So there is some debate about island gold, and so one of the things we want to try to do, the recent research at island gold says orogenic, but Campos and all that worked at Magino think that whatever Magino is, island gold must be, and they think Magino is intrusion-related. So what we want to look, one of the things we want to look at is to see if there's a difference in the quartz trace elements at Magino when compared to island gold, if they're the same or if they're different, and why. And then we have a sample from Ishkode, which is known in Teshoda. And then we also looked at Toro Peru, which is a deposit which is an intrusion-related system in Guyana that's porphyry-like. Also, Ishkode is epithermal, but it's also been overprinted by a orogenic event. And then outside of Superior, most of the samples came from the Maguma terrain in Nova Scotia. So just like the Abitibi, we have a mixture of intrusion-related and orogenic gold settings. The one porphyry copper deposit we looked at is on Cape Breton Island that doesn't plot on here, but that's coxite. So methodology. So we need petrography and CL in order to identify good areas for LICPMS analysis. I would also recommend for CL work, both monochromatic and optical CL, so colored CL. Something that I don't think is really stated explicitly in literature a lot. You do want thick sections when you're ablating quartz because quartz tends to explode in 30 micron sections, so you really want thick sections if you're going to do trace element work of quartz. Larger spot size, fluence, and then a whole suite of elements that we looked at. So the usual suspects, lithium, aluminum, germanium, titanium, but we also tried to see if we could pull apart anything from some of these other elements. I will just say up front, a lot of these did end up being below the detection limit. And lastly, just I guess as a disclaimer, the study wasn't meant to address individual trends in any single deposit. So for the most part, we looked at just a few samples, one or two thin sections from all these different settings. So not really used in to try to differentiate any sort of trends at a deposit scale, looking more big picture. Okay, so just quickly, we have an example of magmatic quartz, so the host rock at Magino. We have an optical CL image and then your regular monochromatic CL image. So for the most part, the quartz, most of the magmatic quartz tends to be this dull, reddish brown looking color, similarly dull in the monochromatic CL. One thing to notice though, the feldspars right here, which show up as this very dull colored monochromatic, they're very bright orange in optical CL. So just sort of highlighting the difference in why you want to couple both of them together, because you do see this also sometimes with quartz. Coxite, or one example of a porphyry copper deposit, has your typical zone CL texture that's usually, I guess, sort of expected in porphyry copper settings. We have Upper Beaver, which is an example of an intrusion-related system. So we see a zoned luminescence, but we also see a uniform luminescence and these cross-cutting overprinting features. So this is also something that could be missed depending on where you take your sample, because in this particular sample, the zoning was very minor. So most of it sort of looked like this uniform. But you do have some remnant zoning, which we interpret as sort of the original texture in these veins, or the primary texture in these veins. So I have another example of Code, intrusion-related system. And so typically what we see in most of these systems at Superior is this sort of reddish, brownish color in optical CL that looks very dull in your monochromatic CL. That just seems to be standard across Superior. One thing to highlight is that even though this grain in PPL, we can see sort of the clear grains and this sort of darker part of the grain, so this grain's been modified, but we do still have the retention of the CL texture. So in PPL it's modified, but the CL texture seems to be pretty much intact. And an example of an orogenic system, we have Goldex in Val-d'Or, so similar to the intrusion-related systems where we just have this sort of dull sort of color in optical CL, and the same thing in the monochromatic CL. So no real zoning for the most part in either of these deposit types in Superior. Macassa, so Macassa is one of the deposits I am looking at a few different samples at. So we have a sample from the main brig at Macassa, and we see sort of that same uniformly dull CL response in the quartz vein here at Macassa from the main brig sample. I don't have an optical CL image for this, but it's most likely that same reddish brown color we see in pretty much every other system. However, in a vein from the SMC zone at Macassa, we do see this beautiful zonation. So in PPL, we have this crystal right here. I should have outlined that, but it's this grain right there in the center. And so we see this zonation in our monochromatic CL. We also still see the zonation in our optical CL. If you change the exposure time, this is a different area, but the same sample, you will see this sort of reddish color become a bit more blue. So we have this blue CL color that's usually indicative, according to Monarchy et al., of higher temperature systems. And then the zone CL, once again, something you typically would expect to see in a magmatic hydrothermal system, which might have some people thinking, is Macassa some sort of magmatic hydrothermal, intrusion-related system as opposed to orogenic? All right, so wrapping up with the laser data, total of 1,200 spots from the varying different settings. So once again, it's magmatic is in magmatic ore deposit type, but magmatic quartz in the igneous host rock. All right, so once again, remind you about titanic hue. So we would expect that we go from, in order of the way these deposits are arranged, we would expect that we go from high titanium to low titanium. So we see our magmatic quartz that plots where it should above all the others. Pegmatites not quite as high as we might expect. Our porphyry copper deposit, which is about right, a little bit lower than the magmatic quartz. Our intrusion-related gold, which spans a range, so we do have some that are elevated, but I would have expected a few more of these, of the quartz from the intrusion-related settings to be a little bit closer to what we see in porphyries. Then we have orogenic, a lot tighter and generally lower, and then we have epithermal deposits about the same. And then let's just show you aluminum, which was the only element that was above the detection limit in every single case. Don't really see much variation, although there is quite a bit of a spread with in the orogenic samples. Moving on to lithium. Lithium is important in some settings, but it is below the detection limit in most, so we can see less than half the samples in intrusion-related settings, for example. But lithium in particular is enriched in the intrusion-related settings from the Maguma terrain in Nova Scotia. So and for those deposits, they are related to S-type granite. So typically you see high lithium in quartz. Usually the assumption is that there's some association with S-type granite. Looking at germanium, see a little bit of a trend, but typically we see this wide range in intrusion-related settings. So most of these outliers and far outliers, they come from Jerome. Not exactly sure what the reason for that. Maybe some germanium-rich country rocks or something from Jerome, which is in the Swayze area. But we also have some elevated germanium data from Ashley and 4K as well. So we looking at Rusk 2012 classification scheme. So we go from a porphyry copper deposit field to orogenic gold field to epithermal. So decreasing temperature, just showing you the pegmatite data there first because it gets crowded when everything else is there. But the Rusk classification scheme just shows that you can classify these deposits hopefully from higher temperatures to low temperature systems. So magmatic quartz plots in the porphyry copper deposit field, which is about as expected. We also see a number of our intrusion-related veins plotting in that field as well. And so most of these veins, they come from Magino in particular, but we also see some data from Kode, Renabe, Ishkode, and Torpuru, so sort of intrusion-related systems. So that is expected, but the overwhelming majority of the intrusion-related systems, as well as the orogenic, etc., plot in the orogenic gold field. We do have a few data points in the epithermal field, including a few points from the one epithermal deposit, Ishkode. So looking below, we do see, once again, lithium enrichment. So sort of just relying at 5 ppm seems to be where there's a break in the data. And so to the right of that line, most of these systems are the pegmatites, which are hiding behind there, and these deposits from the Maguma terrain. But in addition to those, we do also have high lithium from Upper Beaver, Ashley, from Upper Beaver and Ashley that have elevated lithium. So one of the things is, what would be the reason for that? Like, are there S-type granites in that area? No, but what else could maybe be causing this lithium enrichment that we see in places in the Superior province? All right, another classification scheme, germanium over aluminum from Mueller et al. So we do see that they have it, less than 0.08 for magmatic, greater than for hydrothermal. Unfortunately, we do see a spread in the data of magmatic quartz that do span the range of magmatic and hydrothermal, which is unfortunate. You would expect all of them to be over there. The porphyry data does the same, but we do still generally see that most of the data from the orogenic deposits and intrusion-related deposits, they do plot in the hydrothermal field. So looking at this data, one could infer sort of a curve. We go from high titanium through to high germanium, and then lastly, at the lowest temperatures, we have higher aluminum, which would make sense with our epithermal deposits being the lower temperature system. Bottom figure, we have titanium versus lithium. So I subdivided this in sort of a quote-unquote intrusion-related gold field. So we do see our magmatic quartz and the samples from the porphyry copper deposit plotting there, which is good. But we also have those same samples from Magino and some from Kode and also Torpuru and Guyana. So we do see some of our intrusion-related systems plotting in this field. What we also see is we don't see any of our orogenic systems plotting in that higher titanium field as well. On the low temperature end, or the low titanium end, we have the high lithium and low lithium. And so we see, once again, our deposits from Nova Scotia, just for reference, but also our other lithium-rich intrusion-related deposits like Upper Beaver and Ashley. So here we also have a curve, maybe from higher titanium through to low titanium, but higher lithium before finally going through to low lithium, low titanium. And what's important is that all of the samples, orogenic samples from Superior and all the epithermal data plot in this sort of the end of this field, so at the lowest temperatures. So one of the things, because we don't see most of this data from intrusion-related systems Superior, so once again, these are well-classified deposits, why don't they have higher titanium? So one of the things could be maybe some of these intrusion-related systems are really orogenic, or because these are well classified, maybe that later over printing, deformation, metamorphism, maybe these quartz grains were crystallized, and so they lost not only their CL response, but also their chemistry. And then lastly, just to show, even though this wasn't the point of the study, we can, for some settings, pull apart, for some deposits, pull apart different groupings. So Ranabi and Wawa, which is an intrusion-related system overprinted by orogenic. So we do see that our orogenic quartz types plot in one area, and our, orogenic, and then our, I think actually this is the intrusion-related that plots here with orogenic, and then the intrusion-related plots in the orogenic field, and then the actual orogenic veins plot in the epithermal field here at Ranabi. So if we just remove these fields, we still can see two general clusters. So it does show that there is some potential on a deposit scale, maybe with more sampling, to actually pull apart different groupings that may be related to these different mineralizing events. And at Jerome, just to show that we have just one single vein type that we sample at Jerome, but we see a trend, two different trends in this data. So maybe indicating an overprinting event here at Jerome. So conclusions, is CL response useful at determining deposit type? It might be, but still must be paired with trace elements. CL imaging at Macassa might also suggest some sort of genetic complexity, because for all the other deposits in Superior, we don't really see that zonation that is so evident there, at least in the one zone at Macassa. So quartz from most intrusion-related gold deposits doesn't seem to have higher titanium, but we do still see a trend overall looking at the data from high temperature to low temperature. So there still is a potential there to classify these systems. And then just to point out, we do have some exceptions at Code and Magino. So one of the things would be, why is that high titanium preserved, I would say, at Code and Magino and not in some of these other systems? And then on a more deposit scale, we do see elevated lithium in our Upper Beaver samples and at Ashley. So what is the cause of this increased lithium? If not S-type granites, maybe local sedimentary rocks. And the same we could say about Jerome. Why the high germanium in that case? So future work, still have some more laser ablation work to do from deposits like Gosselin, Young-Davidson, and at Macassa, and also some other settings for reference. And then try principal component analysis of all of the data just to see what that pulls out, if there are some differences that might be more obvious. And then SIMS auction isotopes at University of Alberta. Acknowledgements, thanks to my supervisor, Dan Contact, Ross Sherlock and Metal Alert, etc. And if we don't get any questions, there's my email.